We're going to continue on with our discussion of impedance in this phasor domain analysis of circuits that are operating in the sinusoidal steady state. More particularly, we're going to introduce the concept of complex impedance, where we'll see that impedance in general has a real part and an imaginary part and can be represented in either rectangular coordinates or in polar coordinates. We'll then go on and extend our understanding or expand our understanding of series and parallel connections to include impedance, and look at how the concepts of voltage and current division apply with impedances. And then we'll look at delta to Y transformations involving impedances. So we've seen that the impedance of a resistor, Z sub R, is simply equal to the value of the resistance. It's a real quantity. On the other hand, we've seen that the inductor, the impedance of an inductor, is equal to J times omega times L, and it's an imaginary number. And similarly, Z sub C was equal to negative J over omega C, again an imaginary number. And we observed, and let's just reiterate, that the impedance of an inductor is a positive quantity, while the impedance of a capacitor is a negative quantity. In general, we will talk about Z, a complex number, that will have a real part and an imaginary part. The real part we're going to refer to as resistance. The imaginary part we're going to refer to as reactance. And again, a positive reactance refers to an inductive or an impedance that has an inductive nature, and a negative reactance has a capacitive nature. Now, we can also talk about Z in polar coordinates, where Z then can also be referred to as, Z equals magnitude of Z e to the j theta, where the magnitude of Z is equal to the square root of r squared plus x squared, and theta is equal to the arctangent of the imaginary part, the reactance, divided by the resistance. So, for example, here we have a resistor and inductor in series with each other. The net impedance would be then R plus j omega L. If you had a resistor and a capacitor, you'd have R minus j times 1 over omega C squared. In those instances where you have both an inductor and a capacitor being combined, the impedance will be pure imaginary, and it'll equal j times the positive impedance of the inductor minus the impedance of the capacitor. When this quantity is positive, we'll say that the impedance has a net inductive characteristic. When this quantity here is negative, we'll say that the overall effect, or that the overall nature of this combination here, would be net capacitive. Now, there are times when it's convenient to talk about not impedance, but 1 over the impedance. So if the impedance is a measure of the circuit's tendency to impede the flow of electrons, 1 over the impedance becomes a measure of the circuit's ability to conduct electrons. And we refer to that as, call it capital Y, and it's referred to as admittance. It also is a complex quantity consisting of a real part, G, that is called conductance, and J times an imaginary part, B, where B, the imaginary part of the admittance, is called or is referred to as the susceptance, S-U-S-C-E-P-T-A-N-C-E. So we have impedance in polar or rectangular form. We have admittance in rectangular form, and of course it can also be written in polar form also.